Hello student, in continuation to the second lecture on semiconductor laser, we'll discuss about the lasing condition. Okay, and for that again we'll consider the same figure which we have discussed in the second lecture. So we'll refer to this particular figure. Now it is seen that the electron occupy the lowermost state of the conduction band up to the level EF, and here the electron occupies this space. Okay, up to the level EF, and holes occupies the uppermost. Here lies the holes, the uppermost state of the valence band up to the level EFP. Okay, so it is up to this level. There is a hole in it. So in the non-equilibrium state EFN, there is here EFN and EFP. It represents the electron and hole quasi-Fermi level respectively. Now, by virtue of pumping a non-thermal equilibrium steady state is obtained, in which the large density of electrons here and large density of holes simultaneously exist in the same space. So for writing the probability of induced transitions, knowledge of the electron concentration in the conduction band and hole concentration in the valence band is required. So we should have an idea about the concentration of electron over here and the holes over here, because the existence of an electron at an excited level does not assure that there is a hole in the valence band. So it doesn't mean that the existence of electron over here implies that the holes will exist over here. So the probability for transitions are written in terms of Fermi-Dirac distribution function. So if we assume light wave of frequency nu naught, okay, traveling through the junction, the beam will induce A to B transition, say from here to here, okay, during which the light is emitted, as it has been shown in the form of this h nu. So if we transit from here to here, there will be a photon transition, a photon emission. In fact, it may happen otherwise also, that during which the light is emitted as well as B to A. There will be a transition from B to A, which leads to absorption. So it will go from here to here, and there will be an absorption. So the rate of absorption from a group of level levels at energy E nu, okay, we will consider as E nu in the valence band, EV in fact, in the valence band, to a group level at the energy EC. So EV for the valence band, EC for the conduction band. This is the levels. This is the energy in fact. Okay, this refers to valence band. This refers to the conduction band. May be expressed as, so the rate of absorption. So rate of absorption, RBS. Rate of absorption may be given as P into 1 minus FC. F subscript C, E as a function of A into F subscript V, E as a function of B into capital N. Here FC and FV, these two are Fermi function in conduction and valence band, okay, respectively. Capital N, here we have seen here capital N. It is capital N is the density of photons of energy E, and capital P is there. You just have seen here capital P. So capital P is the transition. P is the transition probability. Okay. So the stimulated emission rate. So now we'll write stimulated emission rate R as subscript ST, that is given by P into FC into EA, 1 minus F subscript V into EB, okay, into N, right? Now for emission of light, okay, we have the basic knowledge that RST must be greater than RBS. So if we will consider this one to be equation number 1, this one to be equation number 2, okay. So comparing equation 1 and 2, we find that the emission will exceed absorption if FC E subscript A should be or has to be greater than FV E subscript B. We will compare these two equations. Now using FC, F subscript C into E as a function of A is equal to 1 by, this is from distribution function, 1 plus e to the power ea minus e subscript fn by kt. This will be our equation number 3. Now again, fv, so the next equation will be fv e subscript b will be equal to 1 by 1 plus e to the power e subscript b minus e subscript fp by kt. Okay, so we'll substitute these two equation in equation number 3. Okay, so from there you will get efn minus efp greater than ea minus eb, but we know that ea minus eb will be equal to h nu. Therefore efn minus efp will be greater than in fact h nu. So will be our equation number 4. It also follows that the energy of the photon emitted due to electron transition must satisfy the condition. This condition has to be satisfied. Okay, so on combining equation number 4 and 5, the necessary condition for releasing in the p-n junction become efn minus efp must be greater than equal to h nu must be greater than equal to eg. So this becomes equation number 6. Okay, this condition it was first obtained by Bernard and Differog. Easy and EFM minus EFP constitutes the outside limit of the laser spectra. Now we need to consider the gain in a semiconductor. So the fractional increase in the intensity of radiation of frequency nu per unit, okay, distance traveled within the depletion layer is defined as the gain coefficient per unit length of the semiconductor. Okay, so for that the expression, although it's a very big expression, we need to derive it, but then we can use the same expression which we have in the case of the conventional laser, the gain for the conventional laser. So the gain coefficient n2 minus n1, these are the density per unit volume, nu square g nu a21 by at pi nu square. So this becomes our equation number 7. Now if we assume tau as p, okay, it denotes the spontaneous emission of X-ray. This denotes the time for, in fact, time for spontaneous emission of electron. Then A21 is equal to A tau sp. So we'll just substitute the value of A21 over here. So we'll get now gamma is equal to n2 minus n1 nu square g nu, g is a function of nu rather, 8 pi nu square tau sp. Okay, so in a semiconductor laser, population inversion is not strictly the quantity n2 minus n1. It is actually caused by the injection current. So here what we can again further, you can rewrite this equation, n nu square g nu divided by 8 pi nu square tau, okay, sp. So what we can say is that it is actually caused by the injection current. Here small, which you have seen just in the last expression, small n represents the density of carrier. Now let the current density through the diode be J. So the number of electrons injected per second per unit volume of active region is equal to J by ED, where D is the width of the depletion layer. This number of carrier is removed in the steady state by recombination. So the rate equation governing the steady state is given by dN by dt equal to J by ED minus n tau sp equal to 0. This implies if equal to 0, then J by ED must be equal to, we take this side, n by tau sp. Okay, so So it means that under steady state condition, the rate at which carriers are injected into the active region must equal to the electron hole combination rate. So combining these two equations, we get gamma equal to j v square. This is the v square. Okay, g mu by 8 pi e mu square d. This is v and this here is mu. This is the difference. So this will become your gain coefficient. So from here we'll just stopping this lecture. We'll again discuss optical activity, threshold condition, and few more subsidiary topics or very smaller topic related to semiconductor in the next lecture. Until then, thank you very much.